Alright, so I'm going to do an example, analyze this graph. We'll find out where it's increasing, decreasing, concave up, concave down, extrema, so mins and maxes, and if it has an inflection point or points. So here's my little table. Okay, so we're going to go through this pretending not to know anything about this cubic, even though we know that it's a positive leading coefficient cubic. That's going to kind of look like this. Like, we're going to pretend not to know that, because when we have more difficult problems, we're kind of going in blind, not knowing what the graph is going to look like. So our first thing we can do is find the derivative. We can find extrema by setting those equal to 0. So at x equals 0 and x equals -4/3. So that's where the first derivative is 0, so we have a horizontal tangent at 0 and at -4/3. It's probably going to both be mins and max. I mean, they're probably going to produce mins and maxes. Remember, just because the first derivative is 0 doesn't mean it has a min or a max. It could be right here, and it wouldn't be a min or a max in that scenario. But most times, it's going to produce a min or a max. Okay, let's find our second derivative. And as long as we have our second derivative here, we might as well set it equal to 0, and then we can find any inflection points it has. So all you have to do is set the second derivative equal to 0, and that'll always give you potential inflection points. So -2/3, I say potential because it has to change concavity at that point. So -2/3 comma something is, well, in this case it's going to be an inflection point because it's a cubic, and you'll find that it'd be pretty tricky not to be an inflection point if the second derivative is equal to 0. So our inflection point is -2/3 comma, and if we plug it back in, we get -2.4. So if you're ever asked to find an inflection point, point in math means an ordered pair. An inflection point is not -2/3, it's -2/3 comma -2.4. So that's our inflection point. Alright, so now we can figure out if we have mins or maxes at these two x values. I've got x equals 0 and x equals -4/3. We're going to figure out whether it's a max or a min at 0 by using the second derivative test. So we're going to find y double prime of 0. And all we really want to know is whether it's positive or negative. If I put 0 into our second derivative, it's going to be 6 times 0 plus 4, so we get 4. Okay, so that tells me that it's concave up, because the second derivative is positive at 0. And if it's a concave up, then it's going to be a minimum. It has to be a minimum because it's concave up. So at 0, there's a minimum. So extrema, we've got, I'm just going to put them as ordered pairs for this problem. And there's some sort of a minimum at that point. If I plug 0 into the original, I get 0, -3. So 0, -3 is a minimum. It's for sure a local minimum. We'll just call it a minimum or local minimum. You probably won't be asked to determine whether it's an absolute minimum or a local minimum, so I'm just going to call it a minimum for right now. Because in 4.3 you aren't allowed graphing calculators, so all of this is just going to be analytical process to find out all these characteristics of the graph without a graphing calculator. Okay, so we have one of our extrema or critical points figured out. Now we're going to find the second derivative at negative 4/3. Well, that's equal to 6 times negative 4/3 plus 4 gives me negative 8 plus 4 gives me negative 4. Okay, so the second derivative at negative 4/3 is negative, so it's concave down, so it's a maximum. So at negative 4/3 we have a maximum. So negative 4/3 comma, and we know that's a max. If I plug negative 4/3 I get negative 1.8. We're plugging negative 4/3 into our original function and we get negative 1.8. Okay, so now at this point we've found the first derivative, second derivative, we've done a second derivative test on both of our critical points. Now I'm going to make a sketch. I'm going to make a sketch on what I know. I know that at 0, negative 3 there's a minimum. Okay, and it's going to look like that. It's going to bottom out at 0, negative 3. At negative 4/3, negative 1.8 is a maximum. Alright, so like right like maybe like right here there's a maximum, so it looks like this. Okay, there's no other extrema because there's no place where the first derivative is undefined. Sorry, probably getting dizzy watching this. So to find extrema, you set the first derivative equal to 0 and solve. Find out if there's any points on the bottom that make it 0. There isn't. There's no restricted endpoints in the given problem or restricted domain to produce endpoints. So these are the only extrema possible in this problem. And they occur right here and right here. We know that there's an inflection point at negative 2/3 comma negative 2.4. So right in the middle here, right there is our inflection point. So we know that it's just going to go like this. It's going to be concave down until it gets to the inflection point. So in interval notation, it's going to go from negative infinity to negative 2/3 because that's the x value there. So it's concave down from negative infinity to negative 2/3. That's not an ordered pair, that's an interval notation. It's concave up from negative 2/3 and beyond, so to infinity. We know once you have your graph, you can see where it increases. It increases all the way until it gets to negative 1, or negative 4/3, sorry, that's what that is. So it's increasing from negative infinity to negative 4/3, and then it increases again after it gets to 0. So from 0 to infinity, those are your two intervals in which it increases, and then it decreases from a max to a min. So from negative 4/3 to 0 is where it's going to decrease. Okay, so that's all we were asked to find in this problem, and never had to touch a calculator, except maybe to figure out those y values, which I didn't even show you how I did it. Okay, this is an example of a much more involved problem. I'm not going to go through, it would probably just take too long. If you're in my class this year, I'm posting a picture of this problem. I'm just going to kind of explain it a little bit. So we've got our original function. We find the derivative, which is product rule, and all sorts of things. Set it equal to 0, and we end up getting 0 and negative 4/5. Those are the 2 points in which the two values that produce a horizontal tangent. So I plugged 0 back into the original, negative 4/5 back into the original, and these are my two extrema, 0, 0, and negative 4/5, 0.29. Okay, find the second derivative. Well, this was my first derivative right here. So you could combine these two. It might be helpful to combine them, like do a common denominator and combine them. looks like I just did it as is. So I did a derivative here, which is quotient rule, and then a derivative of this with a product rule. So here's the quotient rule part of it. Here's the product rule part of it. Go through a whole lot of algebra. Here's my second derivative. Set it equal to 0. So I put 0 on this side. Looks like I cleaned that up, moved it to the other side. Set it equal to 0, so right here I combined, moved it over to the other side, did a lot of algebra. Looks like a quadratic formula. We get two answers, negative 1.127 and negative 0.47. So this is not in the domain of the function. You can look at the original, and the domain of this is negative 1 and larger. So x is greater than or equal to negative 1. Anything less than negative 1 will not be in the domain because you'll be taking the square root of a negative number. So this is not a possibility because it's outside the domain. So this is my only x value that produces the inflection point. You can plug it back into the original and we get our inflection point. Alright, so we would have to, at this point, plug 0 into our second derivative and plug negative 4/5 into our second derivative. If you plug 0 in, you get positive, so it's a minimum because it's concave up. And if you plug negative 4/5 in, it's a negative number, so it's going to be concave down, so it's going to be a max. And then you could make a sketch based on what we know. So let's see, we know that at 0, 0, we just said is a minimum, and it's a horizontal tangent, so it's going to be look like this. At negative 4/5, negative 0.29, we have a maximum. So I'm going to go, that's negative 1, negative 2, negative 4/5 is 0.8, so like right in here it's going to be a maximum. Oh, and wouldn't it be nice to be able to see it? Sorry about that. Okay, so we know at 0, 0 we have a minimum, so I showed this. Negative 4/5, comma 0.29, I have a maximum horizontal tangent. If you notice that the first derivative, if you put negative 1 in, it does give you 0 on the bottom. So there's kind of an endpoint at negative 1. If I plug it in, I get 0. So negative 1, we already talked about it. The domain of this one starts at negative 1. So it does produce an endpoint at negative 1. Nothing else happens. We have no other critical points. So this is the graph, a sketch of the graph, because I know there's a horizontal tangent there, and the horizontal tangent at 0, 0. Negative 1, comma 0 is an endpoint. So based on the graph, you know that it's going to be a minimum. It would be considered an absolute min here and here because they both have the lowest point possible. Maximum here, it increases, but it's not an absolute maximum. It increases from negative 1 to negative 4/5 and from 0 and beyond. It decreases from negative 4/5 to 0. There's an inflection point at negative 0.47, so negative, basically a half, like right there. There's an inflection point, so my picture is actually pretty accurate. So it's concave down from negative 1 to negative 0.47, and then it's concave up from negative 0.47 to infinity. Alright, so all based, without looking at the calculator, just kind of making a sketch after you've done all your analytical work.